Hello, I'm Rob and today we will be presenting our work on semi-supervised code switch detection for Spanish English, and we're going to see how close we can get to supervised performances. This work is mainly done by Dana, Sarah and Rasmus, and I am their supervisor. So as you probably all know in this code switching workshop, code switching is the act of using multiple languages within the same utterance. More particular, in this study we're interested in predicting the language labels on the word level, as you can see in the example on the slide. This is a tweet that is in Spanish as main language, but in the middle there is an English noun phrase that is used. And we can also see that we have three labels: Spanish, English and other, which is used for words that are in neither of the languages, like punctuation. Almost all previous work on this task is supervised, so they use standard supervised sequence labeling algorithms to train a model, and they require annotated code switch datasets. However, we propose to relax this assumption and exploit monolingual datasets instead. We call this semi-supervised, as we don't have any manual annotation and we don't have any annotated data for the target task. This would enable to build code switch detection models for many more language pairs. This leads to our two main research questions. For the first research question, we're interested in comparing multiple semi-supervised code switch detection models and comparing them against each other. And then the question that automatically follows is how well does the best semi-supervised model compare to the state-of-the-art supervised models?
In related work such as the Lindsay benchmark, the organizers achieved results higher than 98% accuracy with multilingual BERT and ELMO. In the glucose benchmark, modified multilingual BERT and unsupervised Muse models achieved 96 and 92% F1 score, while semi-supervised character engrams achieved 92% micro F1 score on English-Turkish datasets and CRFs 95% on the same dataset. We used the default train validation and test splits introduced by the Lindsay for our models. The train set is only used by the supervised models that we compare against. Monolingual data comes from Wikipedia articles with 41 million English words and 60 million Spanish words. And we remove emojis, punctuation, and numbers from these Wikipedia articles, and we categorize them as other.
So we used quite a different variety of methods for this. First of all, we tried with word unigrams, which is essentially just choosing the language where the word appears with a higher probability. Next up, we tried with character engrams, which is choosing the language where the joint probability of the characters in the word have the highest probability. And we did a similar thing with word engrams, where we chose the joint probability of the words in the sentence instead. Next up, we tried the Viterbi decoding, which is representing the sentence as a Markov chain where the hidden states are the two languages. And then we have the parameters like initial probability, transition probability, and emission probability. Those were found empirically, and you can see more about those in the paper. Next up, we tried LDA, where we have the topics as the two languages. The documents are the words, and the collection of words in the documents are the character engrams. And the last two methods were more supervised models. Those were SVM and logistic regression, and those were used for creating a decision boundary between the two languages.
To evaluate the performance of our models, we use the F1 score. Viterbi has the overall best performance, scoring 95.99% on validation data. Word unigrams, character engrams, SVM, and logistic regression models achieved almost similar results with a range of weighted F1 score from 19.34 to 92.90%. We implemented majority voting, which did not lead to improvements. We tried with taking into consideration the predictions of all our models, as well as permutations of three models, and we found out that the best results would be from character engrams, Viterbi, and SVM, scoring 93.72%. To see what is the best score we could achieve from our results, we implemented the Oracle ensemble, and taking into consideration all the predictions of our models, it scored 98.47%. Also, comparing Viterbi to the MatchAmp toolkit, which gives similar results to the state-of-the-art model, we notice a difference of around 3% in favor of the supervised model. For the development dataset, all models have a better F1 score for English than for Spanish, and for the test datasets, the other way around. This might be due to a discrepancy between the label distribution of the two datasets. The low performance of the LDA model can be explained by the results of previous studies, which show that when the percentage of the dominating language decreases under 70% of the whole text, the performance of LDA decreases as well. Talking about hyperparameters, for character n-grams, we saw that with higher values of n, we can capture groups of letters that are representative for one of the languages. But we cannot say the same for word n-grams, because the way words are ordered in Wikipedia articles is more formal than that of Twitter posts. For LDA, SVM, and logistic regression models, we tried different vectorizers, but TF-IDF vectorizer performed better as it helps decreasing the impact of very frequent character n-grams.
We found that most of our models achieved promising results, but the best one was Viterbi with 95.99% weighted F1 score on validation data and 92.23% on test data. It still underperformed compared with the supervised matchup model, which gave results as high as 99% on validation data and 98% on test data. We also conclude that assembling has potential.